Okay, hi everyone. I hope we had a relaxing Wednesday. We'll continue with, we'll more or less pick up where we left off on Wednesday, continuing to talk about random trees and using uniform random trees as our template or test case for more general models of random trees. So that means, we've been studying. Oh, I just have to turn off the YouTube live stream. I'm hearing myself talk. One sec. Okay, so we're studying some random tree, which is uniformly random from this set of labeled rooted trees with n vertices. And then we describe this bijection between such trees and sequences of random integers. And then we use that to study the local structure near the root and near a random vertex in T. And we saw that that looked like sort of a sequence of uniformly random trees of random sizes, these Borel distributed sizes, arranged along a large or in the limit infinite backbone. Right. So in the first lecture, in fact, we also got one bit of sneak preview of the global structure of how this bijection could be used to understand things about the global structure of large random trees. And that was when we looked at the asymptotic behavior of the height of a randomly sampled node. So I'm just going to remind you of that and actually quickly go over the proof of the Rayleigh limit once more, just because it's a computation. Well, it doesn't take long and it's a computation I want you to understand because I'm going to do a variety of sort of more involved versions of the same computation. I'd like to have done all the details in the easiest possible case. So we saw that if we take a random tree with vertices 1 up to n and pick a random leaf of that tree, then the height of that random leaf plus 1, or equivalently the number of vertices on the path from the root to the leaf, has the same distribution as the minimum of I and n, where I is the first repeated entry in the sequence V that we got under the bijection. So in fact, so one of the participants pointed out to me that I was missing this minimum before. There's just a boundary case where when the tree is just a single stick with no branches coming off where you can sometimes get the answer n plus n plus 1 for the first repeated entry in a sort of well, in fact, this here. So this is the first repeated entry in a longer sequence. So VI, I greater than or equal to 1. So where we just extend this sequence with additional IID uniform samples from 1 up to n. Okay, so we had this identity, and then as a corollary of this, we stated in the first lecture that if we look at the height of this randomly sampled vertex divided by root n, that converges in distribution to a Rayleigh random variable. Okay, and so the reason for this is something, again, I already basically went over, so I'm just, this should feel familiar from lecture 1, was that if we look at the probability that U is at least C root n, then the distributional identity tells us that this is the same as the probability that the first repetition happens at position at least C root n plus 1, okay, which is the same as saying that we're asking for the probability that the first C root n values in this sequence are all distinct. Right, so here I'm ignoring rounding. Right. right? The first repetition is in position at least C root n plus 1, if and only if the first C root n terms are all distinct. So those last two probabilities are really the same event. So in particular, the probabilities are the same. Okay, so now I think I confused one or two people by being a bit fast in the next step, which is just to say that we can express this probability by Bayes as a product of conditional probabilities. So where the ith term is a probability that the ith vertex v is different from the previous entries in the sequence. So from v1 up to vi minus 1, given that we already know v1 up to vi minus 1 are all distinct. Okay, and so that's just asking for a random sample from 1 up to n to avoid I minus 1 particular values. So we can write that as a product for I guess that should be I from 1 up to n minus 1. So we can write that as a product, then this should be Cn, from 1 to Cn of 1 minus I minus 1 over n. Okay, and now if I simply write this product as e to the sum of logs, then here I have log of 1 minus I minus 1 over n. And a Taylor expansion tells me that this is minus I minus 1 over n plus order I squared over n squared. Okay, and so so this this whole sum here gives me e to the minus c squared on 2. That's the, well, let me do that. Let me write that that's the same as then the sum I from 1 to c root n of I minus 1 over n plus order I squared over n squared. And now that gives me e to the minus c squared on 2 plus order I cubed on n to the half. So that's, sorry, c cubed on n to the half is the error term I get from summing this, this sort of remainder term here. So that's in particular e to the minus c squared on 2 plus little o of 1, provided that the error term there is little o of 1. So, and that's true provided that that c is little o of n to the 6th, or in other words, that c root n is little o of n to the 2/3. Okay, and now the point is that so we have this asymptotic for the probability u is at least c root n, and the answer we got we can rewrite as integral from c to infinity c to the x e to the minus x squared on 2 plus little o of 1. And this is just, that's the Rayleigh density sitting inside that probability. So that's the probability that a Rayleigh, inside that integral. So this is the probability that a Rayleigh random variable is at least c plus little o of 1. Okay, so that proves that u on root n, the cumulative distribution function of u on root n converges to that of a Rayleigh. Okay. Right, so that's all lecture 1 reminders. And now what we'd really like to do is extend this picture, which tells us about what happens for a randomly sampled leaf to a collection of several randomly sampled leaves. So that's, in jargon, that's called studying the random finite dimensional distributions of this random tree. Okay, and the idea of accessing the structure of random graphs, and in particular random trees, by random sampling like this, I think more or less dates to David Aldous in his work on the scaling limits of exactly these sorts of trees. I'm just wondering if someone can, okay, it seemed like I froze there for a second, or someone froze. And my screen share has dropped off. Let me try to fix that. I had some internet connectivity issues this morning, so I hope they don't recur, but if they do, you've been warned. There may have just been a glitch just now. I'm showing that I'm sharing screen, and yet I'm not seeing my share, so let's see. Sorry for the trouble. Just when it was getting good too. Okay, I think we're back in business. Here we go. Okay. So, yay, it's back. Yes. Right. Someone asked where the little o1 term comes from. So the question is, what happens when you sum this error term over I from 1 to c root n? Then you get c cubed over n to the half. And if this is little o of 1, then e to the little o of that can be rephrased as an additive plus little o1 here. I mean, you could write it as 1 plus little o1 if you like, but because this is a constant, it amounts to the same thing. Okay, so now I want to tell you. So that's a random one-dimensional distribution of this large random tree. Now I want to extend that to random finite dimensional distributions. And this is where the term line breaking construction really comes from. So here's how it works. So the setup of this theorem is really, well, it takes a moment, but what it's really doing is describing for you the finite dimensional distributions. So these definitions are worth sort of paying attention to. So we start from a Poisson point process on the non-negative real line. Which is inhomogeneous, okay? So its rate increases over time. The rate function is just linear. Lambda of t is equal to t, okay? And we'll list the atoms of this process in the order they arrive. So as P1, P2, and so on. Okay, so this list goes on forever. And because the rate gets larger as time goes on, we expect the gaps between these atoms to get shorter and shorter. Okay, so that gives us some picture which looks like some initial atom P0, P1, and then P2, maybe P3 is a bit of a bigger gap, but then as time goes on, the spacings stochastically get shorter and shorter. Okay, and this goes on forever. Now let's so what are we going to do with these? I mean, what's this? We need to connect this to the tree. So let's take a uniformly random tree in Tn and list its leaves in increasing order of label. As L1, L2, and so on. And just in order to have, so this is some finite list. There's only finitely many leaves, but just in order to make it go on forever, I'm going to, just for convenience, I'll set LM to be the root of the tree if M is bigger than the number of leaves. Okay, that's just so that I can say that this is defined for all values of M, but I'm only ever going to use a bounded number of these of terms in this sequence, so I'm always with high probability only going to be actually looking at leaves. Okay, and now, so for I at least one, let me look at, actually, I think I'll call this K because that's what I call it later. So for K at least one, write TNK for the subtree of Tn spanned by the root of Tn and the leaves L1 up to Lk. Okay, so this is a tree that we already saw. We saw it in the course of the bijection, because when we went from the sequence V1 up to Vn back to the tree, we precisely built a sequence of trees. We had a first branch which consisted in all of the values Vi before the first repetition, and that branch built the tree T1 for us. And then when we went up to the second repetition, that added a second branch and built a tree T2 for us, and so on. Okay, so these are those same trees. Tn1 is the tree, is just the first branch. Tn2 contains the first two branches, and so on and so forth. Okay, so is that definition clear enough? I mean, I could be a bit more formal here, but since I've already shown this to you before, I feel like I can get away just saying the tree spanned by those vertices. Okay. Then if I look, I'm going to write size of Tn I to mean the number of vertices of this tree. Okay. Then if I rescale by n to the half and the sequence of sizes, then that converges precisely to the sequence of atoms of this Poisson point process. Okay. So this is a start. You start to see where the term line breaking construction at the top of the in the title of the lecture comes from, right? You have this semi-infinite line, and this is telling you that if you're interested in the joint distribution of the line lengths of the tree sizes, then it looks like you get that just by kind of summing up the lengths that you see of these lines in the Poisson point process of these spacings. Okay, so we'll develop that further. Well, in particular, we'll prove the theorem, but then we'll go a little further than that. But let me first remark that this is an extension of the result about the Rayleigh distribution, because if we look at the first atom, okay, if we look at the case K equals or I equals 1 of this statement, so just looking at the I equals 1, right, relates to the size of the tree that just goes from the root to the first leaf. So that's really like the length of that first branch. Okay. Then this is this, right? This result, we proved this result actually by saying that if we looked at the path from the root to the smallest labeled leaf, L1, that the length of that was distributed as the index of the first repeated entry, and so was Rayleigh distributed. But now if we look at the first point of this Poisson process, what's the probability that that point occurs after position C? That's the probability that there's no point in the interval 0C, which for a Poisson process is the probability that a Poisson with parameter, well, we have to figure out what the total intensity is in this region. That's the integral of the rate. Is equal to 0. Okay, so the rate function we said was just linear, so lambda of x is equal to x, and so this integral here is c squared on 2. Okay, and so we're asking for a Poisson with mean c squared on 2 to be equal to 0. That's exactly e to the minus c squared on 2. Okay, so that is to say that P1 is Rayleigh distributed. And so this theorem really extends the previous corollary. Okay. So I saw there was some discussion in the chat, but it seems like everything's been cleared up. Are there any questions about this before I start to go into the proof? So the last comment from Serta that it's the construction that follows from the bijection up to the kth repeated entry is quite useful, because that's really how we're about to think about the tree TNI is in terms of the tree built by looking at the sequence up to the ith repeated entry. Okay. By the way, maybe I should mention, so this there's a version of these slides, not just in the notes, but actually of the written slides already on the course website that I've linked a couple of times previously, and that's linked from the website, the summer school website that Omer is maintaining. So if you want to look back at the slides, you can either download them and look there, or you can go to the YouTube stream and scroll back in the video to refresh yourself on things I've said earlier today. Okay, so right, so we're trying to prove this statement that this vector of subtree sizes converges, and this is I should say this is in the sense of finite dimensional distributions. So that means that for any fixed k, if I look at the vector of the first k elements here, it converges to the vector of the first k elements here jointly in distribution. Okay, so maybe I'll just put that up in the corner as a kind of reminder of where we're headed. But I have a lemma to prove before we prove the whole theorem. So this is what the lemma is the key. We're really just going to compute the exact joint distribution of the branch lengths in the finite combinatorial trees. So for I at least one, let me write dni for the distance in the tree Tn from the leaf Li to the tree Tn I minus 1. So this is equivalently, this is just the size of the tree Tni minus the size of the tree Tni minus 1. Okay, so you know, if the tree went if this was the tree, then right, dn so dn1 here is maybe I'll delete 7. So dn1 here is 3. The distance from this leaf to the root, which is the sort of 0th tree, is 3, and then the distance from the second leaf to the first tree is 2. So dn2 would be 2. Okay. And indeed, you know, when we by computing the distance to the next leaf at each step, that's the same as computing the number of vertices that get added when we continue the bijection up to the next repetition. So it tells us the difference in those two subtree sizes. Okay, so then with that definition, if I fix any integers, any positive integers, g1 up to gk, I can ask, what's the probability that that those distances or branch lengths or differences in tree sizes are given by g1 up to gk? So the probability that dni is gi for each I from 1 to k. And that's, so we have an exact expression for that. It's n following factorial g1 up to gk minus k minus 1 over n to the g1 plus g2 up to gk plus 1. And then all that times the product for I from 1 to k of, let me write j from 1 to k, g1 plus gj minus j minus 1. Okay. So where does this expression come from? Well, we're really just going to think about what it means for the bijection to yield a tree where the jth branch length is, where the ith branch length is gi for each I from 1 to k. What has to happen with the sequence of values v1 up to vn minus 1 in order for this to occur? Okay, so then the rest of, I'll just say, once we have the lemma, the rest of the proof of the theorem really consists in, like in the corollary for proving the Rayleigh limit, just thinking about what happens when these values g are on the order square root of n, and then extracting the asymptotics from this combinatorial expression. Okay, so that's, I will do that, but it's really just a sort of a multivariate version of the one-dimensional calculation we already did. Okay, so let's see why this lemma is true. So in order for dn1 to be g1 and so on, dnk to be gk, what has to happen? Okay, so maybe I should say, so I'm using here the bijection, so with v1 up to vn minus 1 being the sequence corresponding to Tn under our bijection. Okay, so, well, first, this is saying that the first branch has length g1. So that means we must have, so seen values all the way up to g1, and then we saw a repetition. So then after that, when we see a repetition, that means we create a leaf, and then the value, the next value is vg1 plus 1 appears somewhere down here in the sequence. So somewhere down here, there was vi, and that's also equal to vg1 plus 1. That's the first thing that has to happen in order to have the first branch having length g1. Okay, so let me start to do a bit of bookkeeping of what we're saying must happen. So so v1 up to vg1 should all be distinct, and then we need that. So we see our first repeat. So vg1 plus 1 should be somewhere in this set. Okay, and then we need to build a second branch of length g2, which means that we see the next value after vg1 plus 1, that's vg1 plus 2, and then vg1 plus 3. This tree is starting to get a bit messy. But anyway, and so on up to, so vg2, and then there should be a repetition which yields a leaf, and then so that's saying we need vg1 plus 2 all the way up to vg2 are all distinct, right? I mean, and not only these next values need to be not only distinct from one another, but also from the previous values we saw along here. Otherwise, we would start a new branch. Okay, so so really, maybe let me say that, so all of the values I'm writing over here on the left have to be distinct from one another. So these values have to be, all of these values should be different. And then because after this number of steps, dn 2 steps, we're asking to finish a second branch, then it should be that that we see another repetition. So VG1 plus G2 plus 1 should be so somewhere in the set of previously seen vertices. So VG1 plus G2 plus 1 should be in here. Okay, and so on and so forth. So at G1 plus G2. So yeah, sorry, thanks. Yeah. Right. So then, maybe the G1 plus G2 plus 1, it's some previously seen value. It could be here, it could be here. And that has to continue all the way to the end, right? So at each step, we ask for the next branch to consist of some distinct values followed by a repetition, which can be anywhere in the previously seen vertices. So it finishes off with G K minus 1, so G1 plus all the way up to GK minus 1 plus 2, and so on up to V G1 plus G2 plus GK. Those should all be distinct. Okay, and then finally we need that the last value, G1 plus GK plus 1, should be one of the previously seen values. So in here. Okay. So, and thank you for the correction. That should be G1 plus G2 as well. Right. Okay, so this, there's a bit going on here, but it's fundamentally not so complicated. We've got a collection of random variables that all have to be different. And then we've got at k particular steps, we need a certain value to take, a certain random variable to take values in a particular set of things, which are all different by the previous sort of requirement. Okay, so let's call this event the event that all of the things written in black are distinct. A. Okay. Okay, so that's just one event. A bunch of things should be distinct. And then on the right-hand side, we have k different events. Let's call them B1, B2, up to BK. All right, and then I'll call, and I'll let B be the intersection of the BI. Okay. So what we're saying is that under our bijection, what we're asking about here, the probability that this occurs, is precisely the probability that A and B both occur, because we see these particular branch lengths if and only if A and B occur under the bijection. Okay, any questions about that? Or shall we figure out why now it's just a matter, if you understand that, then now it's just a matter of figuring out what the probability that both A and B occur is. Okay, so let's think about that. So how many? So A is not too, well, neither of them are too bad. So A is the event that how many random variables we've got. Notice that we've got, this would be a list of all of the random variables from 1 up to this value here, G1 up to G1 plus G2 up to GK, except that we've removed K minus 1 of them, the ones over here that are supposed to be repetitions. Okay, so that means this is just the event that G1 up to GK minus K minus 1, so independent uniform random variables on the set 1 up to n, are all distinct, right? So that has probability, just using the same sort of Bayes formula product of conditional probability calculation that we did before. We can write that as the product for j from 1 up to that value of 1 minus j minus 1 over n. Okay, and that, or if maybe it's in this setting, it's more natural to write as n minus j minus 1 over n, because then we see that it's precisely n and then this following factorial divided by n to the g1 up to gk minus k minus 1. Okay, so A isn't too bad. And now, what about the, how are we going to compute the probability of A intersection B? Well, let's again use Bayes and think about the probability of Bj. So for j from 1 to k, what's the probability of Bj given that A occurs and B1 up to Bj minus 1 have all already occurred? Okay, so that's right. So that's asking for the one of these values to fall in the appropriate set on the left, given that we've already seen the other relevant repetitions. So that's the in other words, that's the probability that, so V G1 plus Gj plus 1 is an element of the set V1 up to V G1 plus G2 plus so on up to Gj, given that A and B1 up to Bj minus 1 occur. Okay, and now it's important to note here that because if these previous B events have already occurred, then that means we've already seen j minus 1 repetitions. Okay, because the value Vg1 plus 1 wasn't new, it already appeared, and this value wasn't new, it already appeared. Okay, so this set on the right does not have this number of distinct elements because there are j minus 1 repetitions. This set has size, I mean, under this conditioning, this set has size g1 plus g2 up to gj minus j minus 1, because this says that there are j minus 1 repetitions. Okay, and so then we're asking for this random variable to fall in a, so it takes n possible values. We're asking for it to fall in a set of this size. So the probability of that is just the size of the set divided by n. Okay, and so now we just put all of that together by Bayes. We get the probability of B given A is the product for j from 1 to k of probability Bj given A and B1 up to Bj minus 1. So that's product j from 1 to k of this expression. Okay, and so let's compare. So the probability that both events occur is just the product of this and this. So what do we get? Well, we get an extra factor n to the k on the bottom here, okay, which takes this coefficient and changes this minus k minus 1 into a plus 1. And then we get the product of these gj terms, these g1 up to gj terms. And that's precisely what we'd claimed up here. We have the plus 1 on the bottom and the product of the sums of the gi's on the right. Okay, so that's, you have to sort of just think a little bit about what the bijection tells you. But after that, the proof is really a matter of careful bookkeeping to wind up with this expression. Okay, and any questions about that? Okay, well, I didn't set up any polls in advance. I'm wondering if we're sort of at a natural point for a break, but on the other hand, the proof of the theorem is, I mean, follows on pretty naturally. So I'm not sure. Maybe I'll, let's see. Let me take a 3-minute break and answer any questions anyone has. Doesn't hurt to make sure everyone is on board. Okay, seeing no questions, maybe let me just sort of again remind ourselves what the theorem is. So we're trying to prove that this sequence of subtree sizes behaves asymptotically like the locations of the atoms of this inhomogeneous Poisson process, right? So that's our aim. The definition of DNI is still slightly confusing to me. Good. Okay. So let me. I'll just do a quick example and then continue on with the proof. Right. So let's in general, our trees don't have the property that the labels just increase along paths, but just to make it easy to draw trees for the example, it's nice to just label them this way so I don't have to think. Okay, so right, so in this tree, the leaves in order, this is the first leaf, this is the second leaf, this is the third leaf, this is the fourth leaf, right? And so then this is the tree, I guess in this example, n is 14. And so the tree I've just highlighted is Tn1, right? It's this first branch, right? And Tn0 would just be just the root, okay? So then what's dn dn1 is the size of Tn1 minus the size of Tn0. So that's well, that's 6 minus 1 is 5, and that is indeed the number of edges on this path. It's the length of the path, right? And so what's Tn2? Tn2 would be the tree that has these nodes and these nodes. Okay, so it's spanned by the root, and so you take the two smallest leaves now, 6 and 9, and look at their paths to the root. That gives you the tree Tn2. Okay, and so dn2 is Tn2 minus Tn1, which is what, 9 minus 6, which is 3, and that's indeed the number of edges on this path. So on. Does that clear it up? So dn3 would be 2 because we add 2 vertices, or equivalently a branch of length 2 to make the third tree, dn4 would be 3 because we had a branch of length 3 to make the fourth tree. Okay. Right. So so we proved this theorem, which gives an exact description of the joint distribution of the branch lengths in a finite random tree. And now our aim is to show that these rescaled tree sizes converge to the vector of atoms of this. So remember, this is our Poisson point process on 0 infinity with rate function lambda, which is just linear in time. Okay, so so let's start by writing down the joint density of those of the points on the right hand side. Okay, so for positive integer k, the joint density of p1 up to pk is what? So I'll call it f. Okay, and so what does it? What does this mean? We're asking about the density of the event that p1 is at x1, p2 is at x2, and so on up to pk at xk. So we can write that as a product for I from 1 to k of the rate at which a point arrives at location xi. So that's lambda of xi. Okay, so that corresponds to having a point at xi, and then we want no points between these successive times x1 up to xk. So that we'll write as an integral from xi minus 1 to xi of lambda of t dt. Okay, so I'm in here. I'll let me say that. So it's just useful to set x0 equal to 0. Okay, and so this is asking, this exponential, and there's a minus sign missing, is enforcing that there's no points in xi minus 1 xi. Okay, and then we also want, because these are supposed to be the ranked atoms in increasing order, we want that x1 is less than x2, and so on up to xk. Okay, so that's the picture of where is it? Of the joint density for this thing, for the first k of these. Right? We said we want the points to be here, and then we don't want any points here, and we don't want any points here, and each time that kicks in an exponential term. And the product form is just due to the property of Poisson processes that events, the number of points in disjoint regions are independent. Okay, so but now in our particular example, we know these rates. They're so lambda of x is equal to x. So this is the product of so for I from 1 to k of xi, and then we have e to the minus. If we do that, so if we integrate x from or t from xi minus 1 to xi, we just get xi squared minus xi minus 1 squared over 2. Okay, and then we still have this this indicator hanging around. Okay, but that those exponentials telescope. So this gives us the product from 1 to k of xi all times e to the minus xk squared on 2, and then the indicator that the points are in increasing order. Okay, so that's the joint density of the first k points of the Poisson process. And now let's do what I said we would do, which is just work out the asymptotic joint density for these branch lengths on scale n to the half. So if I write, so x not equals 0 still. And then I'm going to take gi, so the g's like the g's from before, to be xi n to the half minus xi minus 1 n to the half. Okay. Then what's the probability that, so Tni has size xi n to the half for each I from 1 to k? Well, that's precisely asking for the differences to have values gi. Okay, so that's the probability that dni is gi for I from 1 to k. And we have an expression for that. So it's this expression from the lemma. So we had that ratio, and then we had a product, j from 1 to k, of g1 plus gj minus j minus 1. Okay, so right, so now we'd like to use the fact that so gi is basically like xi minus 1 times times n to the half to do asymptotics here. So since you know, g1 plus gj is just telescoping, this gives us xj n to the half. Then we have, so let me do this in two pieces. So let me call this thing 1 and this thing 2. Okay. So so the first thing is so we have an n following factorial xk n to the half minus k minus 1 divided by just n to the xk n to the half plus 1. Okay, so that's like up to lower order terms. There's a 1 over n to the k factor just because there's a additive difference of k between the number of terms on the top and on the bottom. Okay, and then we have a product like we saw before in the proof of the Rayleigh limit, which is just a product of like 1 minus I over n. Okay, for I from 0 up to this xk n to the half minus k minus 1. So that's giving us 1 plus little o1 over n to the k, and then e to the minus xk squared on 2. Yeah, that's right. Okay, so that's the first part, and that's similar to what we saw before. And then for the second part, here we have the product for j from 1 to k of xj n to the half minus j minus 1. Okay, so that's basically n to the k over 2. We get a root n out of each term times the product j from 1 to k of xj. Okay, and so combining those, gives what? I guess this is the probability I really want to be thinking about. So this n to the k over 2 cancels half of that 1 over n to the k. So 1 plus little o 1 n to the k over 2. And then we have the product of the xj, and then all that times e to the minus xk squared over 2. And we recognize here the joint density of x1 up to xk for the points of the Poisson process. Okay, right, and this is just like the Jacobian, which tells you that after rescaling by n to the half, you indeed converge in distribution. Okay, so that's so the claimed convergence follows from this. Okay, so I think that's maybe a good time to pause for further questions. So we've now seen that, right, so branch lengths in Tn look like the interpoint spacings in P, this inhomogeneous Poisson process. Okay. And we're going to build on that to understand a bit more about the structure of the tree. Okay. Not seeing any questions for the time being. I want to say, right, so what happens with the n to the k over 2 in the limit? Well, there's an, right, so if you want to prove joint convergence and distribution, right, the claim was about what happened to that after we rescaled by n to the half, right, that we had convergence and distribution to these points pi, right? And so now you just have to ask what happens if you ask for the probability that Tni is at most, that Tn1 is at most y1 n to the half and Tn2 is at most y2 n to the half and so on, then you're summing over a region whose volume is of order n to the k over 2. And so that's a Riemann approximation of this integral on a mesh size of n to the minus a half in k dimensions. Okay, so that mesh precisely cancels out the factor 1 over k to the 2. Right, and Leor has given another explanation in the comments. Okay, so we don't only care about the branch lengths of the tree, we also care about how they connect to one another, and we'll sort of get to describing that in a second. But first, I just want to state a corollary of the theorem, which is it's literally just the consequence of the theorem if we're only interested in how big the tree Tnk is. Okay, so not just in the set of branch lengths, but in that final size. So that thing converges in distribution to a random variable, which is distributed as the square root of a gamma k a half random variable. Okay, so this is, I think, so I'll just tell you exactly what this means. It's a random variable whose density is given by so x to the 2k minus 1 e to the minus x squared on 2 divided by 2 to the k minus 1 factorial on the non-negative line. Okay, and so that's really very easy to see from the theorem, because the theorem tells us that the theorem says that Tnk divided by n to the half converges in distribution to pk. Okay, and what's the density of pk? Right, so that's we're asked. So if we want pk to be around x, then that's saying there should be a point at x, and that occurs with rate x in the Poisson process, and then we should have that the Poisson process has k minus 1 points up to that time. So the integral from 0 to x of t dt should be k minus 1. Okay, so this is Poisson. We're asking a Poisson x squared on 2 to equal k minus 1. So that's that initial x out the front, and then we have x squared on 2 to the k minus 1 e to the minus x squared on 2 on k minus 1 factorial. Okay, and that is exactly the expression we see up here. X to the 2k minus 1 e to the minus x squared on 2 to the k minus 1 factorial. Okay, so there's nothing fancy going on there. It's just recording. I wanted to mention this particular distributional form that comes up because it shows up again in the exercises for today and tomorrow. Right. So now if we want to get at a little bit more about the not just the sizes of the branches or the lengths of the branches, but the way they attach together, then I need one more definition, which is the idea of the shape of a tree. Okay, so or in particular the shape of one of these sampled trees. Okay, so I think this should be the last definition of the day. Then you don't have to hold any more new concepts in your mind. So if I'm given a labeled rooted tree, with leaves in increasing order L1 up to LK, then, so the thing I'll call the shape of T, so this is going to be a leaf labeled rooted tree. Which we build in the following way. Okay, so leaf labeled, before I go into this, this means so that the leaves have labels, but other vertices do not. Okay, so there's 3 steps. So first, we replace each maximal path containing no branch points by an edge. Okay. Second, we relabel the leaves just by their ordering, okay? And then we remove the non-leaf labels. So just to give you a quick example, you know, if I had a tree, let me make it a little bit, tiny bit more complicated. Okay, so if here's a tree T, then what's the shape of T? So there are 4 leaves. Leaf 1, here's the smallest. Leaf 2, leaf 3, leaf 4. Okay, and so we're just encoding the branching pattern. This first step is the key one. Replace the maximal paths containing no branch points by edges. So here's a path with no branch points. Right, the branch points are here, here, and here. Okay, so this orange path becomes an edge. This path becomes an edge. All of the other paths without branch points already were edges. So the pattern we end up with looks like this. Okay, so this the yellow path became that edge here. The orange path became that edge here. And then the leaves get labeled in increasing order of their original labels. So 1, 2, 3, 4. Okay, I'm just suppressing vertices of degree 2 and then doing some relabeling. And I'm also going to, so is that construction clear enough? And I'm also going to want to keep track of the lengths of the paths that got contracted. Okay, so let's say that so for each edge E of this tree, so the tree on the right is the shape of the original tree. So for each edge E of shape T, I'll write the length, which is really, you know, if I need to be careful, I'll write the tree the tree there as well. But the length of E, so this is going to be the number of edges in the path, which is contracted to make the edge. Okay, so let me do that labeling here. So this was all of these were just paths edges already, so they have length 1, and then this path had length 2 edges. This path had length 3. Okay, so that's the labeling by length. Right. So so I'm interested in describing the shape of so when we build this random tree and sample some number of leaves, okay, we get a shape. If we you know, take all of these paths we've been studying and just pretend that there's between branch points we have single edges, that gives us some random shape, and that's a bounded object now, right? Because there's only k. If we only take k sampled leaves and let n become large, the shape remains a sort of finite combinatorial tree, and we can ask what's the distribution of that shape. Okay, and then along with the shape, what are the distribution of these edge lengths? And that's something that has a hope of converging, right? Whereas if we studied this whole tree, then we'd have to, I mean, sorry, the sort of whole sampled tree, T and K, well, for one thing, you know, the labels would run off to infinity. But here we've sort of, because we've kind of collapsed everything down to a finite combinatorial object, we can hope to talk about convergence in distribution for this shape, okay, and for the lengths. So before I get there, I'll just, so that's the last thing I'd like to tell you about is what the asymptotic behavior of the shape of T and K for K fixed and N large. But before I do that, let me leave you with an exercise. This is one of the exercises in the notes. It's not hard. So this is that the number of binary leaf labeled trees with K leaves is 2k minus 3 double factorial. And you might not have seen this notation before, double factorial. It doesn't mean factorial factorial. It means it's like the factorial, except you skip, you only take half of the terms as you go down from 2k minus 3 to 1. So it's 2k minus 3 times 2k minus 5, and so on down to 5 times 3 times 1. Okay, another way of writing that is 2k minus 2 factorial over 2 to the k minus 1 factorial, right? Because this denominator here precisely cancels out all of the even terms on the top. And this is suggestive. This form is suggestive, given that we just saw a 2 to the k minus 1 factorial show up in our expression for the density of T and K. Okay, so that's maybe worth mentioning. So now the last theorem of the day. Okay, says that so for any k at least 1, as n tends to infinity, we have convergence, joint convergence and distribution for the shape of T and K and the set of edge lengths of that shape. Okay, convergence and distribution to some random shape T along with a vector of random lengths. Okay, and so to tell you, so this is convergence and distribution, and to make that a sort of more interesting statement, I should tell you what the limit is. So, so this pair T and XE can be described by its density, which is so right, so the density with which I observe a particular tree and particular weights is just given by the sum of the lengths and then e to the minus the sum of the lengths squared on 2. Okay, and that's over edges of the tree. And then I should really, so what do I need for this to make sense? I need that T, well, so no, so there's content in the next thing I'm going to say. The density, so it has this term which is relevant, which sort of more relates to the joint density of the weights. But then, in fact, the density only gives positive measure to trees which are binary. With k leaves. And also all of the edge weights should be positive or non-negative, but sorry, so there's a question in the chat. E in shape is to say E is a leaf. No, so E is an edge of the tree. So that's what I really mean. Let's see, 2, 3, 4, 3, 2, 1, 0. Right. So what I'm trying to describe here is the distribution of this random shape and then the edge lengths that I get, right? So in this those are these edge lengths, right? So if you imagine that this is the random tree and we were interested in k equals 4, then the shape would be this leaf labeled tree here, and the edge lengths would be this vector of edge lengths here in some canonical order. Okay, but this, you see, I mean, so in general, when you take a shape, it could be, you know, it doesn't have to be a binary tree. It could be a single path. It could be, it could have branch points of degree greater than 2, which would make it non-binary. But part of the content of this theorem says that in the limit with high probability, when we sample a finite number of leaves of this random tree, we only see binary trees come out the other side. And moreover, I mean, the only way that the so this density enforces that we only see binary trees, but it doesn't say anything else about what shape we're likely to see, which means that the shape is sort of equally likely to be any binary tree with k leaves. Yeah. So so I see a couple of points in the chat. There are only finitely many trees with k leaves. Yeah, I mean, so the exercise is related to that. Should there be a scaling factor in front of length e in the pre-limit? Yes, indeed. Thank you. So these should all be multiplied by n to the minus a half. And right, so maybe I should have. Someone asked in the chat, what are the XE? So I should say that, you know, this pair here. So it consists of a random tree and then a vector of random variables. So it's a random. So pair because it has 2 coordinates, even though both of the coordinates are sort of slightly complicated objects themselves. So with density given by this function f here. Yeah. So let's record some. Yeah. So in other words, yes, exactly. So this is the definition of the things on the right. Let's make some observations. Okay, so this says that the shape of TNK is asymptotically uniform on leaf-labeled binary trees with k leaves. And so that in particular means 2k minus, maybe I should say one thing. So there's one, because otherwise what I'm writing right now will be a little bit confusing. So 2k minus 1 edges. So for me, so I'm using the term binary tree here to mean that the root has exactly one child and all other non-leaf nodes have exactly 2 children. Okay, so you know, examples of binary trees are this and this and this. Okay. So these are rooted. Yes, these are rooted trees. So we've maintained. So the shape. When we pass to the shape, we maintain the root. Yeah. No, the root is the root of the original tree. So we didn't reroute when we went from here to here. The root was just whatever the root was before, and the root doesn't. So So then there's the question: why does the root have degree 1? So in general, in the shape of the tree, the root does not have to have degree 1. It's just that in my definition of a binary tree, I'm insisting that the root have degree 1. Okay. So I mean, if I'm doing that, but because yes, I'm doing that precisely because that's all that shows up in the in the limit of these random randomly sampled large finite trees, and it's nice to have a simple name for them. Okay, if you like, yeah, I mean, it's also, if you think of it as an unrooted object, then we're really saying that every vertex has either exactly one neighbor or exactly 3 neighbors. That's by saying the root has degree 1. That's an equivalent characterization of binary trees after unrooting. What I'm doing now is trying to give you a bit more intuition for the statement of the theorem here. Okay, so I'm by recording a sort of another way to think about what it's saying. So the statement, the first bit of intuition I want to give you is that it's saying that the shape of this is saying that when you look at the tree spanned by k leaves and the root in Tn, that it's asymptotically uniform over leaf-labeled binary trees with k leaves, and that's how's that encoded in the theorem? Because we're saying that this shape converges in distribution to a random shape, but the random shape is, so the form of the density on the right, if we only look at the marginal on the random shape, it's just a constant. It only insists that the shape is a binary leaf-labeled tree. That's all it insists on. Okay. Yes. So that's the first point. So the second point is that so conditionally, given the shape, okay, the edge lengths are asymptotically distributed as, well, n to the half times this vector, some random vector xi, I from 1 up to 2k minus 1, okay? And in fact, if you, so the joint density of the xi is given here, and indeed, so there was a comment someone made about how this suggests that the edge lengths are independent of the tree shape. That's exactly right. You know, if I tell you what the tree is, it doesn't change the density of the edges. Okay, so one expression for the joint density of the edges is given here. It's the xe to the minus x squared over 2. Another way to write that, so another description. Let me finish what I was saying before. So shape of T and K is asymptotically independent of the lengths okay, and so the last comment I want to make before giving you a bit of an idea of the proof is that so there's an alternate description of the limiting vector. So xe, e in shape T is as follows. So I'd like to just so that this, you know, it's natural in this statement to index the edge lengths by the tree. Okay, but the theorem tells us that we're always going to be looking at trees that have exactly 2k minus 1 edges. Okay, and the leaf labels mean we can just we can just fix some particular rule for ordering those edges as first edge, second edge, and so on. Okay, so we can always just think about this as an ordered vector of length 2k minus 1, and then use that ordered vector to weight the edges of the tree according to our rule for how the edges are ordered. Okay, so rewriting, so if we rewrite this vector xe as xi from 1 up to 2k minus 1, then so we have the following description of the joint distribution. This is distributed as some value times y1 up to y2k minus 1, where so h is distributed as the square root of a gamma k half, and the vector of y's is a Dirichlet random vector. And is independent of h. Okay, so if you haven't seen a Dirichlet random vector before, this means that so what are we doing here? We're describing the total length by pulling out a factor which is the sum of all the xi, and then looking at whatever the random partition of mass is, the proportion of the mass that falls on each edge. And this saying that those proportions are Dirichlet distributed is just saying that that looks like a uniform partition of mass. So this is the is uniformly distributed on partitions of mass y1 up to y2k minus 1. So all of the yi should be non-negative, and the sum of the yi should be equal to 1. Okay, so this total mass here is a term we already saw before, right? We mentioned up above that the total mass of T and K looks like the square root of a gamma K half. Okay, and so now what I'm saying is, if you take your tree T and K, okay, you boil it down to its shape, which means rather than keeping all of the internal vertices on those edge lengths, you just write down the number which is the total length. And now, instead of doing that, you could say, let's also divide through by the total length. So rather than those lengths being big numbers, we divide through by the sum so that the lengths are numbers between 0 and 1 and their sum is 1. Okay, and those lengths just look like a uniform partition those numbers are equally likely to be any vector of numbers whose sum is 1. Okay, so that gives us a full description of the asymptotic description of the tree T and K. It's like a random binary tree with leaves labeled 1 up to k, and then with these random lengths, whose lengths are a random partition of unity, rescaled up to have this gamma k a half size. Okay, so I wanted to say a bit more about the kind of what's missing to go from. So we had a theorem which already told us about the length of the first branch, and then the length of the second branch, and the length of the third branch, and the length of the fourth, and the length of the fifth. But now, right? So that was the theorem that said if we look at this branch and this branch and this branch and this branch and this branch, that these looked like, the first length was like the first value in a Poisson process, and the second one was like P2 minus P1, and the third one was like P3 minus P2, and the fourth one was like P4 minus P3, where these are the points of the Poisson process. okay? But this next, this sort of more complicated theorem that's describing the whole shape is not talking about those branches in the same way, right? It's taking the tree and it's dividing the tree up at all of its branch points, right? And so it's looking at all of these lengths at this length and 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 this length. I'm just describing all their distributions. So in some way, it's a more refined description of the tree than the one that just comes from the Poisson process. But I mean, it's not strictly speaking sort of a strengthening, because there's sort of non-trivial calculations you need to do to go from either of these pictures to the other. It can be done in either direction, but in both cases, there's sort of a little bit of thinking that's required. Right. I think that answers the question that Lior was just trying to ask in the chat. Okay, so we'll talk a little bit more about the additional steps to go from here to there, from left to right at the start of next lecture. And then we'll sort of build on these ideas to start talking about graphs that are not trees. So what parts of the story can be told once we introduce cycles to the mix. Good. Let me stop the live stream and maybe open up the mics to questions.